So let's continue and let's talk.
How do you say the word intentionally in English? Right? So it's located on the outer edge of the wing's trailing edge. And this one? What's the name of the one located on the inner side? Flap, right? What's the corresponding word in English? Fly, right? What exactly is it used for?
Besides increasing lift, what other uses does it have?
Ah, yes, that's right. It's a component used for increasing lift. We will discuss in detail how it increases lift in our flight principles course later on, and how we should use it effectively during flight. Then, regarding the content of this page, there's a major point I want to emphasize, like, what is it? In my final exams. Every year, I almost always include this question. It's always included. I'll give you an airplane, and I will definitely change some of the planes, then ask you to label them. Well, what are the names of several parts of the airplane in Chinese? And then, how do they correspond to your operations? And then, every year, there are always such chaotic results. And there's a high probability I'll test this again this year, because if you can't grasp this, I really think it's a bit unreasonable. And also, when each of us is doing the pre-flight check, what is one of the things we need to do? It should be to move the controls, right? Moving the controls is to check whether your control surfaces are correct, wanting to. How deadly it is. There have been many incidents in aviation history where control surfaces were connected incorrectly, leading to crashes and fatalities. For example, let's talk about our domestic aircraft. Do you know the Chang 5? Well, you know, the last one that grabbed me on this plane. Its maiden flight ended in a crash. Why? Because during the manufacturing process, 2 control rods were connected in reverse. This caused the aircraft, after taking off, to flip over without the pilot checking, and it scraped along the runway. In the end, the cockpit was completely scraped off.
Originally, everything was...
The celebration banquet is set, right? The last aircraft rolled off the production line. The maiden flight was completed. And this ultimately led to such a result. So I think these are the most basic pieces of knowledge. And if even these can be wrong, I really have to put a big question mark on the flight safety of the person who made this mistake. I think what I'm saying is understandable, right? So I hope that in the future, our students will develop a good habit before flying, right? We need to check whether our operating system is functioning normally, whether the control surfaces are responding correctly, and whether the direction is correct. All right, let's move on to the next step and look at the beauty of the aircraft from another angle. What is the key point I hope students will focus on? What is this part called? What do the students in the back call this thing? Regarding the tail fin, this is a particularly common topic. Many students make mistakes here. What is this thing called for those who didn't respond earlier? Vertical tail, right? What is the corresponding English word? Vertical tail. What is the purpose of the vertical tail fin? I cover acceleration poorly, but I teach the principles of flight well, ensuring stability. It provides directional stability for the aircraft, or you could say it offers yaw stability as well. In short, it serves a stabilizing function. Later, we will analyze in detail why it provides such directional stability. So if you haven't learned it well, or if the teacher's explanation was too poor. In that case, this time we should really remember what it is used for. What is this thing called below? This is called the horizontal tail fin, right? What is the corresponding English term? Horizontal tail. All right. Behavior. This way, students remember these two words, as they are frequently used vocabulary. So further, what is the purpose of this tail? Well, the main function of the tail is to provide pitch stability, nacis, for the aircraft. Alternatively, we will explain this further later. To put it more academically, it has the function of dragging the aircraft's focal point backward. When we discuss aircraft stability and control, we will explain these concepts and how we understand them. It's actually quite easy. All right, let's look further. Let's take a look at the tail and vertical stabilizer, both of which have some degree of mobility, right? So first, let's talk about a simple vertical tail. Part of it is immobile and part of it is movable. What about the immobile part? We call it the stabilizer. Stabilizer. However, sometimes we refer to the entire tail as the stabilizer as well, so I hope you are aware of that. In Chinese, we generally call it the stabilizer, while the movable control surface at the trailing edge of the vertical tail, what do we call it? Close Xiaobing. Do the students in the back not? No? It is called rudder, and the corresponding word is rather. So we also refer to this movable part as the control surface, using the term control surface. All right, now this is the vertical tail, and the horizontal stabilizer of this aircraft is slightly special. As we saw earlier, how does this stabilizer behave when the aircraft is being controlled? It moves entirely as one unit, right? We call this an all-moving stabilizer. And in terms of control efficiency, it is somewhat greater. The corresponding English term is stabilator. Sometimes it's also referred to as a flying tail, and both terms are used. So this is a unique feature of the Prt2 aircraft. Whereas for regular aircraft, like the vertical stabilizer, part of it is fixed and part of it is movable. So which part can be controlled? We call it the elevator. What is the elevator used for? To control the pitch attitude of the aircraft, right? Okay, let's continue. So here, first of all, let's take a look at the relationship between our push-pull rod and the elevator, or rather, the fully movable horizontal stabilizer. This is something that often appears in final exams, and is frequently answered incorrectly, which can be quite frustrating. We can see that with the movement of the control column and the push-pull rod, or when pulling the yoke back and pushing it forward, we notice that the transmission stabilizer rotates, right? This corresponds to our basic control technique when we want to maneuver the aircraft's pitch. We call it the push-pull rod. And sometimes students have to answer questions about this in the final exam. Pulling the rod up or down, these are all quite magical expression. We need to pay attention to the accuracy of our terminology. The rod is pushed and pulled. Then, let's look at the next one. How do you operate the review? You can see when you press the control column to the left or right, or rotate the yoke to the left or right, what corresponds to it? The review caused a deflection, right? Are the directions of deflection for the two reviews the same? They're not, are they? Which one deflects in which direction? It's good that everyone knows they're different today. After we explain the principle later, I hope everyone can remember it thoroughly. What is the corresponding relationship between the rod and the intention? This is what was mentioned earlier about what happens if you get it wrong. It directly scrapes the ground, right? The result is that it directly scrapes the ground upon takeoff. During the exam, some students answered with things like turning the control stick to the left or twisting the control stick to the left. What I'm referring to with the terms for left and right is called pressing the stick or pressing the pedal, right? Next, we'll talk about the operation of the foot pedals. What are we operating with the foot pedals? The rudder, right? Let's take a look. When we press the foot pedals, it directly corresponds to the rudder moving. Similarly, whichever side you press the foot pedal, the trailing edge of the rudder should move towards that side. Why does it deflect? This way. We'll explain this in detail later when we discuss the aerodynamic principles. For now, I just want you to understand the relationship between the rudder and the control input. As for the direction, I hope you will remember it after we introduce the basic control dynamics knowledge later. Besides controlling the rudder, what other uses do the foot pedals have on many of our aircraft? Besides braking, there are other uses. Many of our aircraft have nose wheel steering control. For example, aircraft like the Prt2, 4S-172, and all the mainline passenger jets you will fly in the future have nose wheel steering. So, what is used for steering in a small range? It's all controlled using the foot pedals. Let's take a look.
We can see the rudder turning.
The option should be linked with the nose wheel steering, which can help our aircraft taxi on the ground. Clive. However, not all aircraft have nose wheel steering. When our students go to flight school in the future, many might fly aircraft without nose wheel steering. Do you know which aircraft doesn't have the ability to steer? Aircraft 2 is a very common type that doesn't have the ability to steer. Don't know? The DA-40 aircraft doesn't have nose wheel steering, and neither does the Shanhe SA-60. However, we might fly that aircraft, and it also doesn't have nose wheel steering. So, how do we adjust direction at low speeds when taxiing an aircraft without nose wheel steering? We should use differential braking. That means pressing the pedals, pressing the left and right pedals differently to control the direction of ground taxiing. I hope everyone knows this. It's basic common knowledge. Now let's talk about the operation of the flaps. How do we operate the flaps? So, for the C-28 aircraft, its flap operation is quite interesting. It doesn't use electricity. Instead, it's manually operated by hand. In this way, when you pull up, it's like engaging a handbrake, which corresponds to the process of lowering the flaps. The PA-28 aircraft has flaps with settings of 0 degrees, 25 degrees, and 40 degrees. These three angles correspond to different position selections. How do we choose them? We will introduce this when we discuss flap-related content in the two aerodynamic principles later. Some other aircraft, like the 33172, have wings controlled by electricity. The difference with these is during an emergency landing. If, like in the 3172, you turn off the aircraft's power switch too early during an emergency landing, you won't be able to control the wings. However, with the P-28 aircraft, you can turn off the power switch early, allowing you to manually operate the flaps to assist. This device is very useful for adjusting the landing point. All right, the final operation. This is something we haven't covered in our teaching sessions. But this maneuver is crucial for every pilot. What is it? It's the trim operation. Let's take a look. We can see a hand wheel between the two seats. And when you turn the hand wheel, what kind of changes occur beautifully? The trim tab on the elevator supported by the judges deflects, right? This is called the trim tab, and it is a very important device for our flight process. What is the principle behind it? We will introduce it later when discussing the stability and control of the aircraft. Here I will tell you what its specific function is. When we fly, we don't want to always put a lot of force on the stick. So, when we fly the plane to a stable state, we need to use this balancing method to unload the force on the stick. That's its function. All right. So above, by observing the simulated flight process, we took a tour around the aircraft and focused on discussing some of the main structural components, their names, and their functions. Now please answer the following question. When the pilot tilts the control stick or yoke to the left or right, which surface will deflect? All right, the students answered well. So, what should we choose for this question? We should choose intentionally, right? This question is very likely to appear on our final exam, so I hope everyone remembers well the relationship between your control and the deflection of the control surfaces. The first section is done. In the earlier part, we mainly covered some of the knowledge involved. And later on, we will directly apply these things. Next, we will review some physics-related knowledge. We've all studied university-level physics, right? This part of the content is also very important. First, let's talk about examples and example sentences. This part should actually be content from middle school physics, right? So, force is a reason for changing the state of motion of an object. If an object is in a state where no force is acting on it, or the forces are balanced, what will happen to the motion of this object? Will it stop? Lack of quorum. What should it be? Remain. Stationary or maintain a uniform linear motion, right? So, this is force. The key point we need to focus on is that it is a vector. What is a vector? It has both magnitude and direction. Also, an important concept about force is that it has a point of application. These are all things we learned in middle school. So what are the units of force? The most common unit, the SI unit, is the Newton, right? Then sometimes we use a second unit called the kilogram force. What is a kilogram force? It is the gravitational force acting on a mass of 1 kilogram, which is approximately 1 kilogram force. Sometimes we say how many kilograms of thrust a plane's propeller has, which is actually not a standard expression. What should the standard expression be? How many kilogram forces is the propeller's thrust? Similarly, we also have an English equivalent. The imperial unit commonly used is the pound force. Note that it refers to a force. In this context, well, force is something we are all familiar with, but there is another term that students might not be as familiar with, which is the example sentence. For example, when we use a wrench to turn a nut, if we study the state of the nut, we would say that besides the force acting on the nut, there is also the effect of torque, right? So, what are the key elements of torque? First, we need to have a force, right? Then we need to have a lever arm B, correct? By multiplying the force by the lever arm, we get the magnitude of this specific torque. So we say, torque. What is changed is the speed of the object. What is the purpose of the example sentence? On. What is the effect of torque? It changes the state of the object's rotation. It changes the angular velocity of the object's rotation. So, corresponding to this, torque, the unit we use most often is the Newton meter, which is obtained by multiplying newtons by meters. As for the imperial units, we use pound inches or pound feet. This way of expressing it, like force, is also a vector. On one hand, it has magnitude, and on the other hand, it has direction. All right, at this point we might ask, how do we use a vector to represent it? How do we express its direction? That's it. Some students have already mentioned it, while others might not have clearly understood it during high school or didn't remember it well in university physics. At this point, we hope students pay attention to how we express this kind of historical data with vectors and how we use arrows to represent it in terms of rotation. At this time, we need to use the right-hand rule. Take out your right hand, and the direction your forefingers point to is the direction of rotation, while the direction your thumb points to represents the direction corresponding to the rotational vector. All right, for example, in relation to this, in the example of the nut, if we express it with a vector, which direction should the arrow of this vector point to? Pointing inward. All right, let's ask this second to last row. The second student from the right. Second student, please answer. In such an example, if we were to draw a vector, which direction should it be? We use a key to indicate which direction it should be. Please sit. Which direction should it be? This is a very important basic concept. We use the right-hand rule, right? How do we use the right-hand rule? Which direction do the forefingers point? The direction of rotation, and the thumb points to the direction of the vector, right? So, corresponding to such a rotation, if we draw an arrow, where is the direction of that arrow? It is perpendicular to the plane facing B, right? I hope students who answered incorrectly will pay attention. This is a fundamental physics concept. Now, regarding vectors. There is a very important method of analysis for vectors, which is the decomposition and composition of vectors. So, what is the most common method used for vector decomposition and composition in our high school studies? It's the most used in high school physics. We perform force decomposition, right? We often use this method of vector analysis. Now, in university physics, or in other university courses, besides using it, for decomposing linear things like force, we say that. Besides force vectors, what else do we refer to as vectors? For example, displacement is a vector, right? So, linear motion, let's say, linear displacement can be a vector. But if we have an angular displacement from rotation, can it be a vector? Isn't foot displacement a vector? Is foot displacement a vector? Can such a rotation be expressed using a vector? We just mentioned that displacement is a rotation, right? By using the right-hand rule, we can determine its direction. What about angular displacement? Angular displacement also has direction and magnitude, right? We can similarly use the right-hand rule to express it. For example, let's consider the motion of an airplane, which rotates around two axes simultaneously, including a 20-degree pitch around the y-axis, and a 34-degree roll to the right around the x-axis. We just discussed whether rotation is a vector, didn't we? It is a vector, so vectors can be combined through vector addition. This means that when our airplane simultaneously pitches up 20 degrees and rolls 34 degrees to the right, we can actually use vector addition to combine these into a rotation around a single axis, right? In this way, we can achieve the exact same effect. So, what does this correspond to in practice? The effect of rotating 40 degrees around the axis we obtained. How do we get this 40 degrees? The Pythagorean theorem, right? You multiply the squares of the two angles, y, and then take the square root, y, and you can get the angle of rotation, y. So, what does this correspond to? It corresponds to rotating 40 degrees around the third axis we obtained through vector addition. This gives us the direction and magnitude of the combined motion. No problem, right? So, this is the process of such a motion. Therefore, in our course, besides using vector addition and decomposition for force and displacement, we will also use it. For example, with angles and angular velocity, we will perform vector addition and decomposition for rotational vectors. Once our students understand this concept, there will be no need to ask why when we discuss it later. Additionally, we need to mention another topic, which is the translation of reference points for examples and example sentences. This is a fundamental concept learned in university physics, for instance. So for an object at point A that is acted upon by an upward force F, if I want to change the reference point at this time, I ask, if I take point B as the reference point, then how should we conduct the analysis? So, corresponding to reference point B, what is the specific load at this point? How should we conduct the analysis?
Come! The student lying in the last row. Sorry to disturb your sleep, but this is a fundamental concept in the knowledge that follows. I'm asking you, at the initial moment, where is the point of action of the force? If I want to consider this reference point for B, how should its load be? Can you answer me? If you can't answer, then I hope you can. Listen carefully. So, B, if I translate it, then for B itself, the magnitude should remain unchanged, right? When analyzing point B, in fact, from B's perspective, it is also subjected to a force of magnitude F. But at the same time, due to the change in the reference point, we also need to provide an additional example. So, how should we calculate the example of a force of magnitude F acting upwards at point A on point B? Force multiplied by the lever arm, right? So, what does it correspond to? It should be directly F multiplied by a lab. This is when it is subjected to a single force. How to reference the translation? Then there is another situation. Our object is only subjected to a single moment. So let's say this object is subjected to an example of magnitude M, or M. And at this point, I change the reference point from A to B. How do we analyze it at this time? The point of action of the angles, so the example can be moved freely for an object. Understand? Oh, our students can try a simple experiment after class. For example, let's say we are subjected to such a pair. The action of such a pair of forces can correspondingly form a moment. No matter how I change the reference point, the two, ultimately, the moment formed by these two opposing forces should be the same. You can try calculating it directly and see, okay? That is to say, when the force is moving, we should consider not only the effect of the force itself, but also what other forces. What else should we consider? We should also consider the effect of an example, right? And what if it's just an example? Direct translation, right? What's the use of that? Let's consider analyzing the effect of lift on the judges. All right. So at this point, when the plane's judges apply an upward lift force, what is the effect on the plane's center of gravity as a reference point for the plane's movement? What effects does it have? We directly use the method we mentioned earlier. First, what should we do? Can the force be translated or can it not be translated? What should we do then? Okay. So if we change the reference point and consider it from the perspective of the center of gravity, we should first move the force over, right? At the same time, add an additional moment. This additional moment should be the force multiplied by the lever arm. Correct. That is to say, at this point corresponding to the center, if we are to analyze it, we first need to consider the effect of the force, which should be downward. The effect of negative lift. At the same time, it also generates a moment. The direction of this moment is to make the aircraft pitch up. No problem, right? Okay, so the next step is to consider the concept of work and the law of work. What is work? Under the action of a certain force, the distance an object moves is called the work done by this force, right? Specifically, it should be force multiplied by distance, and the unit of work is joules, with the corresponding dimension being newtons times meters, right? Now, if we consider a special situation, suppose an object
where the direction of the force and the direction of the displacement are different. What should we do? We should decompose the force, right? After decomposing, we should consider the component of the force in the direction of the displacement multiplied by the magnitude of the displacement, thus obtaining the work done by the force, right? All right, then what is another situation? That would be rotation. So how do we consider the work done by rotation? In fact, it's similar to the linear motion we discussed earlier. It should be using the torque multiplied by the angular displacement of the rotation. Then what you get is the work done by the rotation. In other words, besides linear motion being able to do work, rotational motion can also do work. Furthermore, if we perform a certain amount of work over a period of time, what do we get when we divide the work done by this time? It's power, right? It reflects the rate at which we do work. So we have discussed some basic physical concepts above, and I hope students can remember them after class. If you've already forgotten them in university physics, because these concepts will be frequently used in our subsequent courses. Then let's review some situations regarding the airplane. When we study flight performance, we often consider the four forces acting on the airplane. Generally, there are four forces acting on an airplane. Yes, we also believe gravity, lift, drag, and thrust, right? So, the study of our flight performance mainly focuses on the effects of these four forces. We will conduct some interesting analyses and discover issues that our students might not expect. For example, what might those be? I want to ask everyone, during level flight and during climb, when is the lift greater? It's exactly the same. When the airplane is in steady climb and steady level flight. This video concludes here. Thank you for watching. All right, let me tell you, no one got it right. It can't be sustained. During climb, the lift is less than during level flight. Why is this? Later, when we discuss the process of flight performance analysis, we will provide a simple derivation. At that time, we will understand that the lift is actually greatest during level flight. During climb and descent, the lift decreases, meaning our lift is reduced. So, the reason an aircraft can climb is not due to additional lift, but because of the engine's thrust. These topics are part of what we will cover later in flight performance. These are very interesting concepts. We will introduce them to you later. What else will we introduce to you? When we talk about aircraft stability and control, we will focus on the aircraft's rotation. How do we describe the aircraft's rotation? Our aircraft has three axes, right? The first axis is the longitudinal axis, which we define as the axis running from back to front. What do we call the aircraft's rotation around the longitudinal axis? It's called roll motion, and the corresponding English term is roll. Then we also have the lateral axis of the aircraft. The direction of the lateral axis is defined from the pilot's perspective as an axis running from left to right. See, the aircraft's rotation around the lateral axis is called pitch motion, right? The corresponding term is pitch. And finally, the last axis, the vertical axis, points from top to bottom. What is the rotation around the vertical axis called? It's called yaw motion, corresponding to the English term yaw. When we later discuss the rotation of the aircraft, we will use these concepts. This also serves as a review of the covered knowledge, and I hope our students will pay attention. So, during the flight of the aircraft, how can we know how much the aircraft has rotated? What do we do? We will have some parameters to express how much these rotations occur. What kind of parameters should we use? The first parameter is the pitch angle of the aircraft. The pitch angle represents the angle between the aircraft's longitudinal axis and the horizontal plane. We will use the Greek letter theta to represent it. So when we are flying the aircraft, how do we know what our pitch angle is? Attitude. First, we should observe the external horizon to understand our relative position to the ground with the aircraft. So, what do we do when visibility is poor? We will choose to observe the instruments. What kind of instruments do we use? We should use the attitude indicator, right? We observe through this kind of gyroscopic attitude indicator, and by reading the distance between the horizontal line and the artificial horizon, we can determine what our pitch angle is. For example, when the aircraft's nose is up, the pitch angle should be a positive value, and when the nose is down, the pitch angle is negative. These are the two scenarios. This attitude indicator corresponds to the one used in general aviation aircraft, and there is a slight difference compared to the attitude indicator used in large commercial airliners. The second parameter we are very concerned about is the aircraft's roll angle. So, what is the roll angle? It specifically refers to the angle between the aircraft's plane of symmetry and the vertical plane corresponding to the aircraft's longitudinal axis, which we denote as ya. When our aircraft is in level flight, what should the spatial angle be? It should be 0 degrees, right? So how do we observe this? We will similarly observe it through the attitude indicator. However, it is important to note that the intelligence of small aircraft and large aircraft is slightly different. Notice that the position of the pointer will be slightly different, right? There will be a small difference between the inner and outer circles. Here, what is given is a pitch angle of positive 5 degrees and a roll angle of positive 30 degrees, which corresponds to the attitude when rolling 30 degrees to the right. I hope students can roughly understand this. Finally, we have another commonly used expression for relative angles, which is the angle relative to the airflow. We call this the side slip angle. Sometimes, when there is excessive side slip, we might also use the concept of yaw interchangeably. It's enough for us to have a general understanding. The side slip angle refers to the angle between the direction of the incoming flow and the plane's symmetry plane, which we denote with the Greek letter beta. If the incoming flow is blowing from the right side of the plane, it corresponds to a positive side slip angle. How do we generally observe the side slip of an aircraft? We usually use a slip indicator to observe it, right? Small aircraft have a dedicated slip indicator, and we observe the small ball inside it. Under normal conditions, if side slip occurs, the ball will deviate. As for why it deviates, we will provide a simple explanation when we cover that part later. On larger aircraft, since electronic displays are used, we need to observe the difference between the triangle and the square. This way, we can understand the current side slip condition of the aircraft. So this is about the aircraft's side slip indicator. Next, on a glider, there is a special accurate method, which involves placing a piece of yarn directly in front of the windshield. By observing the angle at which the yarn swings with the wind, we can also determine the aircraft's side slip angle. In fact, among all indicators, this type of indicator is the most accurate. We will provide a specific example. Later on, in some special situations, sometimes the ball being in the center does not mean the aircraft is correct, right?
When the ball is off center, it might actually indicate that the aircraft is in a no-side slip condition. We will give a detailed explanation of this when discussing single-engine failure. All right, next, let's take a look at aircraft operation. What kind of effect does aircraft operation have? When we push and pull the control stick, what kind of operation are we performing, and around which axis?
Please don't hesitate. It's a pitch control around the horizontal axis, right? So if we operate by pulling the stick to maintain a certain angle, how will the aircraft respond? When we play flight simulators, we might not perform an operation and then observe the aircraft's long-term response. Let's take a closer look, because this will be a key focus when we later discuss the stability and control of the aircraft. In the cockpit, the aircraft is currently in steady level flight at a constant speed, and when we focus on observing the aircraft's attitude, we usually look at the windshield and the relative distance to the horizon. Let's take a look. You can see that once the operation is maintained, there is initially a change in angle, observed through the windshield. How is the distance between the windshield and the horizon? It changes, right? So what happens after the aircraft first pitches up? It moves away, right? And then we see that after a period of oscillation, it starts to pitch up again, right? So why does this phenomenon occur? We will introduce it in the stable operation of the aircraft later. And this is not to be operated. The next operation is the roll maneuver. So what is the main purpose of the roll maneuver, I ask? Please just stop playing. We use the roll maneuver to change the roll angle of the aircraft. And what does the magnitude of your operation affect? Do any students have an idea? What we actually affect is the aircraft. The angle of rotation.